Good morning. First, I would like to thank the organizer for the invitation. We'll be discussing today some work I have been doing in collaboration with the nuclear physics group of the Universidade Federal Fluminense with these people. Okay. The pointer doesn't work. Okay. Okay, good. Well, I will be discussing today fusion reactions involving weakly bound nuclei. Well, first, what's a fusion reaction? It's a process where a projectile with 80 nucleons collides with a target, and then the system surmounts the Coulomb repulsion and fuse to form an equilibrated compounding nucleus that decays through the emission of radiation, light particles, or even fission if it's heavy enough, okay? When a weakly bound nuclei collides, the fusion process is much more complicated because there are several different possibilities. In addition to the usual fusion process where the whole projectile is absorbed by the target, there are other fusion processes that follows the breakup of the projectile. First, there is the possibility that the projectile breaks up into two fragments. For simplicity, I'm considering only projectiles that break up into two fragments. Well, there is the possibility that it breaks up and then each one fuses with the target sequentially. This process leads to the same compound nucleus as the one that is formed when there is no breakup. And from the experimental point of view, this process are the same. So it's called complete fusion, and experiments measure the complete fusion cross-sections. But in addition, there is a possibility that one of the breakup fragments fuses the target while the other one does not. And this is called incomplete fusion. Of course, there are two possibilities, incomplete fusion of fragment 1 and incomplete fusion of fragment 2, okay? Determining the complete and incomplete fusion cross-sections is a great challenge both for experiments and for theorists, okay? However, there are many measurements, mainly for light weakly bound nuclei like lithium-6 and lithium-7 with different targets, okay? Lithium-6 has a very low breakup threshold, it's 1.47, and lithium-7 is more tightly bound, it's 2.45. There is also a beryllium-9, which has a low breakup threshold, but we won't discuss this nucleus because it breaks up into 3 fragments, and then the description is much more complicated, okay? There are data for several targets, mainly heavy targets. Well, from the theoretical point of view, the problem is also very complicated. Several theoretical methods have been proposed. The earliest ones were based on classical physics or semi-classical physics. In classical physics, the projectile was treated as a two-particle system bound inside some potential, and then the motion is classical, and when it gets closer to the target, the two potentials merge, and the fragments can go from one nucleus to the other. There are also semi-classical methods in which the relative motion of the projectile is treated classically as a time-dependent problem, but the intrinsic state of the projectile is treated by quantum mechanics. There are more recent approaches that quantum mechanically based. It uses the continuous discretized coupled channel method, which I will briefly discuss. I could mention the work by Hagino and collaborators and Dias Torres and collaborators. There are other approaches, but I'll be concerned with a recently developed method that we did in collaboration with the Universidade Federal Fluminense. Okay? Well, let's briefly discuss some basic ideas on theoretical description of fusion. Fusion is a very complicated process. The states involved in a fusion process cannot be described by coupled channel method or by this simplified method of a single channel. However, it cannot be neglected because a considerable part of the incident current is lost to the fusion channel. Then one has to take into account the influence of fusion on the scattering wave function. And this is usually simulated by the inclusion of an imaginary potential in the Hamiltonian. When one does that, one loses unitarity, and the diffusion cross-section can be evaluated indirectly because we do not describe the fusion process itself, but it can be evaluated by the lack of unitarity. So one usually expands the wave function in partial waves, and this involves a fusion probability, which is expressed in terms of S matrix, or equivalently by an integral of the imaginary potential with the density. This is a very simple situation where the intrinsic state of the collision partners do not affect the fusion cross-section, but this is not the usual situation. In typical situation, one has to include the excitation of intrinsic degrees of freedom in the collision dynamics. And then one usually does is to apply the coupled channel method, where the total wave function satisfies this Schrödinger equation with a potential that contains the kinetic energy of the relative motion, some intrinsic Hamiltonian expressed in terms of a few intrinsic degrees of freedom, usually collective excitation, and with some coupling interaction. And then one expands the wave function over the intrinsic states, and then insert the expansion in the Schrödinger equation and take scalar product of each intrinsic states. Then, using the orthogonality of these states, one get a set of couple equations. Then there are codes to solve this set of couple equations, and one can evaluate the cross-section for the different processes. The situation is more complicated when one deals with weakly bound projectiles. In this case, the set of states of the projectile includes the breakup channel, which means including the continuum. And then one gets with an infinite number of states, and this is very complicated. When one describes a collision of a weakly bound system, one usually uses a potential that is a sum of the interaction between the clusters and the target, and this is the potential that is used in the full Schrödinger equation. But as I mentioned, one has an infinite number of states, and then what one does is to approximate the continuum by a set of wave packets. These wave packets, which are schematically represented here, is an integral of some weight function with the scattering states. And the shape of this weight function depends, can be different things. In most codes, one uses an histogram, but there are other calculations that use continuous functions. Well, if one discretizes the continuum, then the expansion, channel expansion, has a finite number of states, and the problem is reduced to a typical problem of coupled channel equations. Well, then one splits the channel space into components, one in the continuum and one in bound states. And these wave functions, these components, are used to calculate complete and incomplete fusion, okay? With the continuum part of the wave function, one evaluates a fusion cross-section, since it is, with the bounds part of the wave function, we evaluate this direct complete fusion cross-section. Since I'm using the wave function of the bound space, we cannot have separate absorption of each fragments. And this gives what I called earlier as the direct complete fusion cross-section. On the other hand, taking these integrals with the two potential using continuous states, one gets the absorption cross-section of one fragment and the other fragment. However, what we are getting here is not what is measured, because an experiment gives the complete fusion cross-section, which includes both direct complete fusion and sequential complete fusion. On the other hand, incomplete fusion cross-section is not these quantities that are calculated here, because these are inclusive cross-sections, namely the cross-section 1 is the cross-section for absorption of fragment 1 independently of what happens to fragment 2. That means it includes incomplete fusion of fragments 1 and also sequential complete fusion, okay? And the same goes for the other component of the absorption of the other potential. Then we have the task of using these quantities, that is all one can get from the coupled channel approach. One should extract from them the cross-section which are actually measured. And this is not possible with the continuum coupled channel methods alone. One has to make further assumptions to this purpose. And that is what the method we develop does. Okay. Well, first we carry out expansions, angular momentum expansions, and of the cross-section of inclusive capture of fragment 1. And when one does that, one gets the inclusive probability of capture of fragment 1, which I denoting as P1 of J for each angular momentum. And the same with the other, for the other fragments. Then we use classical probability theory, saying that the probability of incomplete fusion of fragment 1 is equal to the probability of capture of fragment 1 multiplying the probability of no capture of fragment 2. That is 1 minus the probability of fragment 2. And similarly, we define the incomplete fusion probability for fragment 2. And the sequential probability is simply the product of the two probabilities. Okay? And then one inserts these probabilities into the partial wave expansion, and one gets the cross-section for complete fusion. Complete fusion, we sum the sequential probability we just got with the direct probability, and that should be compared with measurements of complete fusion. And using those probabilities, we can evaluate in complete fusion of the two fragments, which can be compared with the data. Well, we have applied this method to several collisions, mainly lithium-6 and lithium-7. We have done also some calculation for helium-6 or beryllium-11, but I want to discuss specifically these calculations. And in our calculation, we use the São Paulo potential to describe the interaction between each fragment and the target. Note that this is a bare potential. It doesn't contain any effective channel coupling effect. It comes from a systematic treatment of the interaction. It's a folding potential with some peculiarities. And as imaginary potential, we use a short-range imaginary potential to represent the absorption of the fragment by the target. We used it in several calculations, and the overall agreement with the data was good. Okay? I'll give just a couple of examples. The collision of lithium-6 with tin 124 and lithium-7 with bismuth 209. I'm showing the results in a logarithmic and a linear scale, and you can see that the agreement between theory and the experiment is okay. All right? What one can observe in these figures is that the green dashed line represents the result of a calculation with the São Paulo potential between the target and the projectile. And we see that the effect of the low breakup threshold of the projectile resulting from the cluster structure with low binding energy is to enhance the cross-section below the Coulomb barrier and to suppress it above Coulomb barrier, okay? This enhancement is easy to understand. If one considers the cluster structure with a low binding energy, the density is spread over a wider range, and when I calculate the folding potential, the barrier comes lower. And then this enhances the cross-section at sub-barrier energy. And the suppression above the Coulomb barrier comes from the fact that if one has breakup as the projectile approaches the target, then complete fusion can only take place in a two-step process, which is less likely. Then the cross-section is reduced, okay? Well, we have reasonable agreement between theory and experiment, but for a better assessment, it's convenient to look at the whole set of calculations and data and to see if one can, the theory can, if one can find systematic behaviors of the cross-sections and see whether the cross-section, the theoretical cross-section can explain these behaviors. And then one wants to compare cross-section for different systems. But this is a complicated problem because the energy scale changes completely when the Coulomb barrier changes. One energy, we cannot compare cross-section at same energy because one energy can be well below the barrier for one system and well above for the other. And then the cross-section for this reason may differ by orders of magnitude. And then to compare cross-sections of different systems, one usually has to reduce the cross-section. Reducing the cross-section means to apply transformations on the collision energy and on the cross-section themselves, so the influence of the barrier is removed. This can be done by several methods. We have been using for many years a method that we call fusion function, the fusion function method, which is based on the Wang approximation for diffusion cross-section. But as we are concerned with the cross-section at above energy, which contains the dynamic effect of decoupling, we will use another reducing method that we developed a couple of years ago. It is what we call the classical fusion function. The idea of a reducing method is that what is an ideal reducing method? It should be a method that makes cross-sections alike when no channel coupling effect is present. So what one expects is that in the absence of channel coupling effects, one would get some sort of universal function. And this classical fusion function method is based on the classical approximation for diffusion cross-section. Okay? The classical approximation for diffusion cross-section, which is written on top of the transparency, is obtained by assuming the partial wave expansion, that if the energy is higher than the barrier for a given partial wave, then the system fuses, and if the energy is lower than the barrier for that partial wave, it is reflected. So it is a classical approximation for the transmission factor through the potential barrier of the interaction of the radial equation, which includes the Coulomb term, sorry, the centrifugal term, okay? So if you do that, one gets a simple expression for the cross-section because the sum of the partial wave become an arithmetic progression. But to get to this expression, one has to do something else. One has to assume that the radius of the Coulomb barrier is the same independently of the angular momentum. That is, for any partial wave, the barrier remains at the same value as the S-wave barrier, okay? This is not a very good approximation, especially for light systems. But this approximation can be very much improved if one replaces the radius of the S-wave barrier by some effective barrier radius, which is some sort of weighted average of the barriers. We did that, we showed that it works fine previously. And what happened is that to evaluate this average barrier, one has to do some complicated calculation, but we found that this average barrier can be given very accurately by this pocket formula written up there, okay? So when we use this effective radius, barrier radius, then the cross-section is very close to the cross-section of a quantum mechanical calculation without any classical approximation, okay? Well, before we use it to compare the complete fusion results that we have, I'll show you that this method does work. What means it works? Means that if we take the cross-section of one channel calculation for different systems, we get the same cross-section independently of what the system is. Well, the reduction procedure, if you look at the expression up there, you see that the quantity within the square bracket is what we take as the reduced energy. It's 1 minus VB over E. And if we divide the cross-section by pi times R effective square, one gets the this universal function, which is simply a straight line with angular coefficient equal to 1. So what one expects is that results from a one-channel calculation reduced in this way will fall on top of this straight line. And it does happen. These are the reduced cross-section. Fine. This is the reduced cross-section we evaluated for several systems at different mass ranges, and you see that the results of the reduced cross-section falls really on top of this straight line, which we call the classical fusion line. Okay. The question is, this is a result of calculation, but what happens if you apply it to fusion cross-section of tightly bound system? If our assumption is right, one should get results that are again close to this classical fusion line. And these are, for some reason, the straight line disappears, but it is just on top of the data. Okay. So we see that in collision of tightly bound nuclei, the experimental cross-section reduced in this way follows this straight line with angular coefficient 1. Then what one wants to do now is to compare cross-sections, experimental cross-sections for weakly bound nuclei, and the cross-sections calculated by our method. We want to put all in the same picture using this reducer procedure. And then one gets these results. At the left, we are showing results for lithium-6 on several targets. And on top are experimental cross-sections, and below are the cross-sections calculated by our method. What you can see is that the cross-sections follow very closely a straight line, but with an angular coefficient smaller than 1. In the case of lithium-6, that dashed line is a coefficient, angular coefficient 0.58. And the data are closely following this behavior. And the calculated cross-section shows the same behavior. To the right are the same procedure, but for lithium-7. Again, we get the same overall situation, but now the data and the calculation follow a straight line with a larger angular coefficient. This comparison leads us to a few conclusions. The first is that the agreement, the overall agreement, if one considers the whole set of data, the agreement between theory and the experiment is quite good. The second is that the suppression increases as the binding energy of the weakly bound projectile decreases. In the case of lithium-6, which has a breakup threshold 1.45 or 47, I don't know, it is the angular coefficient is 0.58. That means a suppression of 42%, okay? In the case of lithium-7, which has a larger breakup threshold, the angular coefficient is 0.7. That means a suppression in this case is 30%, okay? Another very interesting consequence is that we are showing results for targets with atomic number ranging a wide interval. We go from 10, which is 50, to 83. So there is a very large variation of the atomic number. So what this suggests is that the results, the suppression effect does not depend on the target. It's not affected by the charge. So this strongly suggests that the mechanism that is producing the suppression is nuclear breakup and not Coulomb breakup. It may be surprising because Coulomb breakup is very important in the breakup cross sections. But it happens because the breakup cross section gets contribution for very large angular momentum. But then the Coulomb interaction is dominant. But the fusion cross section only take place for small angular momentum, while you have to include a few hundred partial waves in a calculation of breakup. The calculations of fusion converge with 30 or 40 partial waves. And in these partial waves, the nuclear breakup is more important. Okay, just to finish, the conclusions are what I have just mentioned. And future plans includes taking into account excitation of the target, which the CDCC method, we use the Fresco code, doesn't allow directly. And we want also to extend the calculation for systems that break up into 3 pieces, and to do some calculation for lighter nuclei. Thank you.
So thank you very much. Carlos?
Can you show that formula again with the 1 minus VB over E?
What?
The formula you had with 1 minus...
Yeah.
Can you show it again?
Yeah.
Okay, yeah, you passed by. You passed by. Go forward. You went too fast. Go forward. You went too fast. No, it's not this, Felipe. 1 minus VB over E. The formula you had is not here.
This is a probability.
No,
the probability
no.
of something
No,
not happening is 1 minus the probability of it happening.
No, Felipe. Can you go forward slowly? Not very fast.
Forward.
No, slowly. One more. One more. One more. One more. Yeah, here. So you invoked partial waves when you talked about this, the first formula on the left at the top, sigma f. But the way I understand is that you have pi r squared, and it should not be pi r squared because of the small Coulomb repulsion. So if you make r is equal to 1 minus the Coulomb displacement, which is VB over 2E, and when you raise r squared, the 1/2 goes away and you get that. So you don't have to invoke partial wave. You see, it's just the Coulomb repulsion close to the
classical
r.
expression
Yeah.
is pi over k squared, the grazing angular momentum square.
Right.
Okay?
Yeah.
This is, you get trivially by doing the sum of partial waves.
Right.
But if it does not involve the energy directly, and the relation between the grazing angular momentum and the energy is not trivial, because you have to couple the equation. It has, the barrier must have a minimum at that point, and the energy should be the same as the barrier height. So it's a bit...
No, it's very simple. If you have, it cannot fuse if it doesn't pass through that area there, pi r squared. And it will not pass in grazing collisions
You are
because
meaning,
of Coulomb
you
repulsion.
are talking about the
Well, anyway.
asymptotic expression, pi r squared.
Yeah, well, we can discuss this.
Okay.
Yeah, maybe we can follow up on this also later. Tobias had a question.
Is a surprise. And I was surprised with the results of the complete fusion with this classical model of probabilities. And I will explain why, and simply I don't know the answer. I always thought to have the 2 fragments to be absorbed by the target, you needed an absorptive 3-body interaction. That, of course, is fully quantum mechanical. No? But it seems that is much more simple than that. I mean, this Rangel formula, and I don't understand why.
No, the CDCC approach is not a three-body, it's not rigorously equivalent to a three-body approach. It's a simplified version of it. But you're talking about the classical expression or our method itself?
Classical expression for
This is
complete function, that you multiply the two
Oh,
probabilities.
okay.
And it seems not. But I continue puzzled. I mean, I understand that fitting is good. Maybe we'll go back to the
Okay.
discussion. Thank you.
So any other questions? And if not, let's thank Luis again.